I will look at 3 problems. How's that?
Okay, 59.
Okay.
59? There was 59 questions?
Funny. Write the electron dot structure for the covalent compound C2H6. Right? Actually.
What number are we doing?
Number 5.
Thank you.
Copy. We'll see if I am competent enough to do this.
If you're
Insert.
not confident enough to do it, then why do we have to?
You're not using a Surface Pro and trying to copy paste.
Oh, I thought you were talking about the problem. I was like, wait, why do we have to do it? You should get an iPad, they're easier to use.
It's true.
You have a watch,
You have Apple products, only have Apple.
Because this is a work thing. Okay, write the electron dot. We got it right there. So let's start with, we have let's get to a pen. We have a carbon and a carbon. And then we have like that. That's drawing without any dots, right? And then we have to look at what the electron dot structure is. What is the electron dot structure actually doing? Showing the valence electrons. So how many valence electrons does a hydrogen atom have? 1. How do you know it's 1?
Because there's only like 1 proton, so that's the first shell.
Okay. One answer is because there's only 1 proton. So you only have 1 electron. And it's in the first shell. That's a perfect answer. But what if I ask you how many valence electrons does potassium have? Potassium is K. It's in the first column, the 4th element there. It still has 1 because they're lined up in order of chemical properties.
Isn't that what the red numbers are?
Excuse me?
Isn't that what the red numbers mean?
No. Those are actually numbering. Remember having groups and periods? Those are just numbering the groups. And then the black numbers are numbering the periods. It is, it doesn't work that way because you have different numbers in each row. But the first column all have the same chemical properties, which means they all have the same number of valence electrons, which is 1. And then the second column is 2. And then you have all those ones in between that are the transition metals. We're not going to use this with those probably. And then boron has 3, carbon 4. So those columns you follow down. And helium is the only one that isn't going to follow this rule because helium has 2 valence electrons and that fills its shell. All the rest we just put 8 for the complete. So hydrogen just has 1. So I'm going to draw each of my hydrogen's electrons as red dots, and I'm going to put those dots on the side that is toward the carbon. So there I have all the hydrogen valence electrons. Now, how many valence electrons does carbon have?
4.
4. And how did you know that?
Well, a little trick that I use is to do like the 1, 2, and then 13, 14, 15, so just do 3, 4, 5, and it goes to 8.
Okay, that's actually a good trick. She just said, okay, so 13 doesn't have 13 valence electrons, but if I just take the 1 off, take off the 10, it's going to be correct for everything except for helium.
Or you count how far away it is from having an 8 valence.
Okay, so Hosanna has 2 good methods. The reason that you just subtract the 10 is because that's how many there are in the transition metals here in this section. That's filling a D shell, which holds 10 electrons. So looking up there at the top and taking the 10 off, I hadn't even thought of that. To me it was always just knowing, how many electrons for the second row, basically. So that's a good learning thing I'm learning from Hosanna here. So I'm going to draw the valence electrons for carbon with blue dots. Now, do you remember when we put them in, we generally put 1 on each side? And so I'm going to put 1 here. Now this is almost complete. The only thing that's incomplete, and I love that I can do this, is that I don't have my bond with carbon right. How many electrons do I show around each carbon? 7. But that's because the carbon is bonded to the carbon. So I'm just going to take this and scooch it on over. Up too far. Okay. And now I have my carbon sharing those two. And now you can see that I have a bond here, and it's just a single bond represented by these 2 electrons that are shared. Another bond here, those 2. Another bond here, those 2. And so I've overwritten my color coordination to show my bonds there. It would have been better if I had not done that. That's how you do the electron dot structure. Now this was a little more complicated than what I did in class before, because we have a whole lot of bonds. But each bond was the same difficulty as what we did. What in the world did you do? That,
I think there's a chemical reaction.
okay. Way to tie it into class. Okay, so do you understand how we did this, Hannah? No? Do you understand how we did the electron dot structure? Yeah. It's Amber.
So if we don't, like if we write it how you had it at first, where they were like more separate, and we just draw a line and say bonded, we're gonna get points off, or do you want them like that?
You do want to show that those 2 electrons are coupled together. So I smashed mine too close together. I should have put them a little farther apart.
But will that work?
I can't see from here.
Maybe we should get glass.
Maybe you should talk to me after class. All right. Next problem. What's our next problem?
3.
Rank these compounds in order of increasing boiling point. No harshness.
Some of us are overachievers and have homework on Sunday. No, I didn't finish it on Sunday. I finished it last night. The answer's in the book, though. Literally.
For reasons I have no idea, it won't let me change the size of this. So I'm going to have to insert another page or something. Oh, because it's 6. Yeah, I understand.
You're an overachiever. You get mad if you get an A minus. Like, what?
All right. So we need to rank these compounds in order of increasing boiling point. So what did we learn is going to affect the boiling point? It's not the size. Remember we talked about the forces that hold molecules to other molecules. And if you have a stronger force, then it's going to take more energy to break them apart, and it's going to have a higher boiling temperature. So what we're really ranking these is by how strong the force is between one molecule and the next molecule. Go ahead.
Isn't that having to do with how close they were? Because I was confused.
That was the bonds between 2 atoms. It was ionic if the electronegativity was quite different, and covalent if it's not. But now we're looking at what we're going to have between them. So what were the 4 different types of intermolecular, forces between molecules?
Is that like the dipole?
Right. We had, what was the strongest one then? Yes. Strongest was ion dipole. Then we had dipole. And finally, ran out of space there. So since this is strongest to weakest, That's still blue. How is the boiling temperature, boiling point, going to relate with these bonds? The strongest bond has what? The highest or lowest boiling point? So this would be the highest boiling point, and this would be the lowest boiling point. So we just need to look at these molecules and determine which ones are going to have a stronger force between them. Now, if you look at the first one, fluorine, F2, is that a dipole or not a dipole? How would you know? By asking me. Unfortunately, on the test, I would not tell you. Sorry about that.
Well, the definition that you gave us is the attraction between two dipoles.
Well, let's think about this here. Let's go back to what Grace said, because what Grace asked about actually is relevant to this, because the dipole is talking about the bond between the molecules, or between the atoms in the molecule. So if one atom has a higher electronegativity, it wants electrons more, and one has a lower electronegativity, what's going to happen is the one with the higher electronegativity is going to have more negative charge. The one with the lower will have a smaller charge, or a more positive charge then. And so if we look at F2, now that F2 didn't come through, it should have a subscript 2. F2 is 2 fluorine atoms. F bonded to F.
Which would make it really strong.
Well, I'm not talking about the strength of the bond here. I mean, I think it is a strong bond. But which side is pulling electrons more is the question we're asking. Neither. They're pulling the same amount. So in terms of a dipole, what's the dipole moment of this? None. It's not a dipole. Because each atom is pulling electrons with the same amount. So if it's not a dipole, which kind of force can you have between the fluorine, between those molecules of fluorine? Only one of these 4 types can you have if it's not a dipole. No. Which of the 4 types, the 4 blue types of bonds can you have if it's not a dipole? Induced dipole. Induced dipole is the only kind it can have. So the fluorine is going to be of this type. So that fluorine is going to have the lowest boiling point. Now, if there's other ones, then we'll have to compare. If there's another one that's induced dipole, we'll have to compare. And fluorine will probably still be the lower boiling point, even if we did. We don't. Now let's look at the next one, HF. Hydrogen is on the left column. Fluorine is the last column before the inert gases, noble gases. So which one is more electronegative, fluorine or hydrogen? Fluorine is. That means fluorine wants the electrons more. So if we make a molecule that is HF, we're going to have the fluorine is negative and the hydrogen is positive because the fluorine is more electronegativity. It's pulling more electron to it. So now that's a dipole. So which of these forces would I have between hydrogen fluoride molecules? Not ion, because we're just bonding one of these to another one of these. Neither of them is an ion. So it's dipole-dipole. So that's going to be a fairly high boiling point. And what about hydrogen chloride? What does hydrogen chloride look like? Which one's more electronegative? Chlorine or hydrogen? Chlorine, because chlorine is once again in that halogen column. So once again, I'm going to have something that's dipole, and so I'm going to have a dipole-dipole. So now I have to decide which is stronger, which dipole is a stronger dipole, the one with HF or the one with HCl? To answer that, you say which one, they both have H, so we don't have to worry about that. Which is more electronegative, fluorine or chlorine? Fluorine, because fluorine is the most electronegative of all of our elements. So that means the fluorine is going to be a stronger dipole, or the HF is a stronger one. And so even though both of these are in the dipole-dipole, we should have HF has the highest, and then HCl, and then F2. Now, of course, the astute student will go ahead and look up and see what the boiling temperatures for each one of these are. I'm not going to do it right now because we're in class, but trust me, for my solution that I'm going to post for you, I'm going to look up to make sure what the numbers actually are, so we can make sure that our theory here, because this was all based on theory, matches the actual measurements. So if you just put that order, how many points are you going to get on the homework? I'll give you 1 out of 10. You have to have the reasoning there. Why is the FF going to have a much lower boiling temperature? Why is the HF going to have the highest boiling temperature? You have to have a reason.
If you say because of the dipole strength, is that reasoning?
Yes, but you have to have a reason why the dipole strength is stronger for one than the other. Right? If you just say, well, because HF has a stronger dipole moment than HCl, then I say, well, how do you know that?
So then it would be based on its
Electronegativity.
Wait, can you just say that, oh, it's a dipole-dipole, this is an induced dipole, blah, 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 blah? Or do you need to explain how you got that too?
You need to say, so here's what you need to have written down. You need to have F2, this is a non-polar molecule because each of the atoms has the same electronegativity. And thus it bonds by induced dipole, which is the weakest given at the lowest boiling temperature. And then HF and HCl are both dipoles because fluorine and chlorine both have higher electronegativities than hydrogen. And so they're going to bond by the dipole-dipole method, which is much stronger. And then you say, because fluorine is more electronegative than chlorine, then the dipole moment is stronger for the HF than it is for HCl, and hence you're going to have a stronger bond between the HFs than you do between the HCl. So that's what needs to be explained. You can just go to the recording. Okay, I said I'd do 3, even though we're 20 minutes in. I'll stick to my word. One more homework question? Okay. Grace was the first person to ask us, and she said 12. 12 it is. Copy. Insert another page because, of course, I'm putting in page manipulation, insert. It's always dangerous doing these when I haven't read them recently. A 16-gram sample of methane, which is CH4, with a 16-gram sample of oxygen, O2, in a sealed container Oh, is combined. I was like, that's not a sentence. Upon ignition, what is the maximum amount of carbon dioxide, CO2, that can be formed? And that gives us the equation. So I'm going to rewrite this a little bit. Here's our chemical reaction. Actually, I'm going to change that. I'm going to put numbers in blue so we keep them separate from the components of the molecule. Now, this is something that's in today's lecture. So it's a reasonable one to go fast because I haven't lectured on today. Yeah, it's in today's lecture. So we start off with, this is a chemical reaction. And one of the things that you have like the last problem is balance these equations, is balancing to make sure that your equation makes sense, that you have the same number of each atom on each side. So let's do that first. So I'm doing some lecture work that wouldn't necessarily be part of doing the homework. How many carbons, how many hydrogens, and how many oxygens do I have on the left side of my equation? Okay, one carbon. That carbon right there. I swear I changed the pen to black, but. So for the hydrogen, we have 4 of them. Whoops. 4 of them because we have an H with the subscript 4. And then for oxygen, now to make sure everybody's down with this, O2 is 2 oxygens. And we have 2 sets of that. So that's where we have 4 oxygens. Now let's go to the other side of the equation. How many carbons do I have? 1 again. How many hydrogens do I have? I have 2 H2s, right? So that's 4. And how many oxygens do I have? Uh-oh. We have a disagreement.
Because there's 2 subscript.
There's 2 there. And there's the other 2. So it's a balanced equation because we have the same number of each type of atom on each side of the equation. So that's what you're going to have to do for the last problem. I think it's the last problem, isn't it? Actually, I've got it right here. Yes, for the last one. You have to go through and balance it so you have the same number of atoms on each side. So this one here, we didn't have to balance it. It gave it to us, but want to make sure we go through and we understand how to do that. Now, the second is upon ignition. Now, what is this? Okay, this here is not going to stay. What does that arrow mean?
That it's going from the left side. It's a reaction.
Yeah, it's a reaction that goes from the left side to the right side. And so what is this reaction? It tells us in the problem it's combustion, it's burning. So we are burning CH4, which has a common name of methane, with O2, oxygen, and producing CO2. What would our naming convention say CO2 is? Carbon dioxide and water, H2O. Now our cars don't burn methane. They burn longer chains of carbon and hydrogen. We call those hydrocarbons. But that's basically what's going on with your car when you're burning gasoline. You're basically producing carbon dioxide and water. You ever notice water dripping out of the tailpipes of the car? I used to think that that was gas, like raw gas that went through. But it's actually water that is being produced when you burn the gasoline in your engine that then is condensing, forming back into the liquid state. It was in a gaseous state when it was burned, but as it cools, it can condense to a liquid state. So that's actually just liquid water. Not pure water, of course. There's always going to be impurities around. Okay, so now we haven't done anything for the question. We've done something that's important to be able to process the question. So the question asks us, upon ignition, what is the maximum amount of carbon dioxide that can be formed? So if we had 16 grams of methane, I need to take it from grams and say, how many moles do I have? So how do I calculate how many moles of methane I have?
1 mole over the sum of methane, or like how many moles are methane.
Okay, so first we need to calculate the mass of 1 mole of methane. So the mass of 1 mole of methane, we have the mass of a mole of carbon, plus 4 times the mass of a mole of hydrogen. And how do we get those masses? We look back at our periodic table. And to make our life simple, we just use integers here. We're not going to use, if you want to do it right, you take the numbers in the bottoms. So for instance, H is 1.00795. That's its atomic mass. And O is 15.9994. And C is 12.0108. Right? That's how we would do it correctly. But those are all really close to integer values. And so we're just going to use the integer values to save ourselves a lot of time and headache. So carbon has an atomic mass of 12, yeah. Yeah. Actually, we'll take the numbers in the bottom. I forgot. We can't use the numbers in the top because those are the number of protons. But we're going to round off the atomic masses. So carbon is 12 plus that 4 is still just a number 4. And then hydrogen is 1 because there are 4 hydrogens. And our units here is grams per mole. So 12 plus 4 times 1 is 16. So 1 mole of methane, of CH4, has a mass of 16 grams. And at this point, probably I totally don't remember any of this. That's because it was going to be part of today's lecture. Fortunately, we're getting it here now, so you'll be able to do the homework problem. So now we look here and it says that we had 16 grams of methane. If we have 16 grams per mole, how many moles of methane do we have? N for methane is going to be the mass of methane divided by this, I'm going to put capital M, the mass per mole. So the mass we were given was 16. And what we just found for the atomic or the molecular mass, 16 grams per mole. Well, 16 divided by 16 is not a hard math problem. 1. So that's 1 mole. MOL is the abbreviation for mole. MOLE is the full spelling. I wrote it as the full spelling. So we have 1 mole of methane. Now, I really wish that I had used a longer piece of paper so I could continue on down, but I can't. I use a small piece of paper or screen. Now we have to do the same for oxygen. So oxygen. The mass of oxygen for 1 molecule of oxygen is 2 times, well, what is the mass of a single oxygen atom? So Bryson, you're closest. If you look up there, I went through them while you were gone, I think. It's what? The bottom center number is the atomic mass? Yeah. It's 15.9994 if I remember from when I walked out there. So 16 grams per mole. So 2 times 16 is 32 grams per mole of O2. So then the number of moles, of O2 is going to be the mass of O2 divided by the molecular mass of O2. So we were given 16 grams divided by 32 grams per mole. How many moles? 1/2. So we have a half mole of oxygen, and we have 1 mole of methane. Which one is going to limit our reaction? Which one's going to run out first? Oxygen. And if we make a half mole of oxygen and completely convert it, how much methane are we going to convert? Actually, not half, because it requires 2 moles of oxygen for every methane that's used. And so the amount of methane used is going to be half the number of moles of the oxygen used. So I'm going to have 1/4 mole of methane is going to combine with 1/2 mole of oxygen to give me, and notice for every mole of methane, I'm going to produce a mole of carbon dioxide because we have the number 1 in front of them, each one of them. And so that's going to give me 1/4 mole of carbon dioxide. And then since I have a 2 in front of the H2O, it's going to give me twice as much. So 1/2 mole of water. So this reaction is going to use up 1/4 mole of my methane. It's going to leave 3/4 moles of methane uncombusted because there wasn't enough oxygen to burn it. Now, looking back at the question one last time, upon ignition, what is the maximum amount of carbon dioxide that can be formed? So it doesn't say what units, right? So I could say 1/4 mole, and that's a correct answer, and I can't mark you wrong if you put 1/4 mole. But I do want to go one step further. What would the mass be of that 1/4 mole? How would you find the mass of 1/4 of a mole of carbon dioxide?
You combine the masses for carbon and oxygen.
Okay, so the first thing we do is just like we did for the methane and the oxygen. Carbon dioxide is going to have a carbon, 12, plus 2 oxygens. Well, we just did 2 oxygens, it was 32. So 12 and 32 is 44. So 1 mole of carbon dioxide is 44 grams. If we have 1/4 of a mole, what's 1/4 of 44 grams? (44 divided by 4). 11, yeah. So we would have 11 grams. So you can either say 1/4 mole or 11 grams, but you have to show the work that is below that line. That's the work that has to be done to determine how much you're going to have. And of course, these numbers on top here are also important. That's how we got the fact that it's going to be 1/4 mole after we calculate how many moles of each we had. Okay, that one was a little more difficult, right? If you have questions, I do have to at least pretend to lecture, but if you have some questions about it, feel free to email me or come by my office, right? I am trying to be very accessible to students to help them understand and to help them get them right with understanding. All right. So we, in theory, are going to learn about things like catalysts today. Let's see how far we get. Oh, look, put an extra page in. I have a couple things left over from acid that are important. So first, thinking about our acids and bases. What does the pH tell us about acids and bases?
How acidic it is.
Okay, specifically, if I tell you something has a pH of 10,
Then it's more basic.
then it's more basic because 10 is a bigger or smaller number than, and give me the reference.
Bigger number than 7.
Bigger number than 7. A pH of 7 is neutral, a bigger number is basic, a smaller number is acidic. So we have this understanding of pH, and it has to do with whether it's donating donating acid. Acids donate. Donating a proton or accepting a proton. So bases accept, acids donate, or BAAD, or bad mnemonic. So acid rain is a real problem. It was a really big problem in, 70s or 80s because of industrialization. You have places like up in Michigan where they built lots and lots of cars, and they use lots of coal, burning that coal. And when you burn the coal, it releases SO2 into the atmosphere. And then that SO2, when it combines with oxygen, produces SO3, and the SO3, when it combines with liquid water, produces H2SO4 in the water, which we call sulfuric acid. And so when they had acid rain, they had sulfuric acid raining down. Sulfuric acid is typically what you have in a car's battery. That's the acid used in the battery. Battery acid. So that's kind of bad. Now it's going to be fairly dilute, but if the pH is lower than 5, it's considered acid rain. And what is acid rain going to do to things? It will dissolve some things. Remember in our lab last week, we had one test where we put vinegar in, and if it bubbled, then we knew that it was something that contained carbonate. Because the acid will dissolve that carbonate. What else contains carbonate? Marble. Marble is metamorphized calcium carbonate, or metamorphized limestone. And so marble will be dissolved by acid rain. So I have another slide here for another reaction, one that is probably more of a concern today to most people. Rising atmospheric carbon dioxide levels produces carbonic acid. So that's another way you can have some acid in your rain. But here's an example of I was going to say totem pole, but that looks more like hieroglyphs, doesn't it? And what happens over time because that rock has been dissolved. And there's something else we don't think about as much, trees being damaged by the acid. So acid rain, I think we can all agree, that's bad. That's bad for the environment. Well, here's some things that are kind of cool to know. If you have acid rain and it falls into a creek or a lake, a creek.
So.
I don't know why, but I actually learned to say creek as a kid.
I did too. Are you from the north?
I am from California.
Oh, I don't know that.
I was seeing Lindsay's shirt and I was saying, yeah. I didn't say it out loud until now, but yeah. If you have limestone, that limestone will kind of buffer things. When we say it buffers it, the limestone will react and keep the pH from getting more acidic. And so the limestone starts getting depleted though. So you see the reaction here. The hydronium reacts with calcium carbonate, limestone, and produces water, no problem there, and carbon dioxide, and then free calcium. Well, that carbon dioxide, we have a lot of carbon dioxide in our water. As temperatures rise, the water can't hold as much carbon dioxide, and the atmosphere gets more carbon dioxide in. So people who study old atmospheres, they use carbon dioxide levels that they find trapped in air bubbles as a proxy to tell them what the temperature was. Because if it was higher carbon dioxide, it was higher temperature because higher temperatures produce more carbon dioxide in the air. And so if that goes on, you start leaching out any of that calcite or limestone, calcium carbonate, and eventually you get rid of it all. When you get rid of it all, you can't buffer anymore, and you'll start having an acidic pond, and the tree here is dying because the pond is now acidic. So you can handle a little, but if you get too much acid, you run out of the buffering material, and then the pH starts rising. Or excuse me, starts dropping because acids are lower pH. Now, oceans, look at the ocean pH. Is that an acid or a base? It's a base. So the ocean can absorb a lot of carbon dioxide, which is good. In fact, it's vital for life on this earth. Our understanding is the reason our earth doesn't have a runaway greenhouse effect like Venus is because we have these oceans that will take carbon dioxide out of the air, combine them with calcium, and form calcium carbonate, or this is showing a carbonic acid and calcium carbonate forming, and I don't know what to call that. But it takes the carbon dioxide in the air. Once it gets into the ocean water, it then will form into a rock. And so we have huge amounts of carbon dioxide that have been taken out of the atmosphere and formed into rock. So the Earth's atmosphere has much less carbon dioxide than it naturally would have if we didn't have water. And so the theory is it never got cold enough on Venus for liquid water to form, and thus Venus never had this possibility of encapsulating carbon dioxide, and it's been left in its atmosphere, giving it its runaway greenhouse effect. So Venus is far too hot for us to live or survive because it has such a thick atmosphere. We are just right. Okay, chemical equations. We have just finished going over a balanced chemical equation. So a balanced chemical equation needs to have the same number of atoms on the reactant side. And when I say number of atoms, I mean number of hydrogen, number of oxygen, number of carbon, etc. It's not just like, well, there's 7 atoms here and 7 atoms here. They have to be the right ones, as it has in the product side. Now notice the names. Reactants are things that are going to undergo a reaction. Products are things that you produce after the reaction. This pictorially is very nice. It shows 2H2 means I have, that's not enough contrast. Means we have 2 of those H2 molecules. 1 O2, we usually don't write this one, it's implied. Means we just have 1 O2. Then over here we had 2 H2Os, so, 2 H2Os. So the picture makes it clear the prefix number is telling us how many molecules we have. This subscript here tells us that each molecule has 2 atoms. I've already talked about that enough. Here is a pictorial question for you to determine if this is a balanced reaction. Now, how would you know from this picture if it's balanced or not? What would you have to do? What would you have to do? Count them by color. Right? You can't just count the number of them. You have to make sure you have the right of each color.
It's not balanced.
Why is it not balanced?
Well, looking at the blues, there's more blues on the right than there is on the left.
Okay.
And I'm pretty sure I counted right on the reds, but the red ones.
Right. On the left, I looked at the reds. On the left side, the reds have 2. On the right side, there's 0.
There's like orange and then there's like
This color here.
Yeah.
On the screen here, it's red and the others are purple. Projector may not match the screen. So this is not balanced because I could prove it with just the reds. I could look at the blues. The blues, I have 2 blues here. I have 4 blues here. If I do the greens, I have 2 greens on each side. Why did that not stay? And then if I look at the purples, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 purple. Sorry, I actually have a color to go with that. How many on this side?
13 on the other side.
And so 2, 4, 6, 8, 10, 12, 14. No, it's 14. So the number of atoms was the same on both sides, but they were different types, so it's not balanced. Question, Jessica.
Do we have to have PTQ?
Turn to PTQ, but I won't lower you for originality because we have such a small section we covered. So tell me, is this balanced? Unfortunately, this is very similar to one we just finished that was given to us balanced, but is this balanced? I say very similar, I mean.
Yes.
Yes, because it's exactly the same equation we just finished doing for the homework problem. The only difference is the positions of the molecules are switched. So this is balanced because you have the same number of each atom on each side. We've already gone through all of this. This is the work we did for that homework problem, so I'm skipping right over it. Reaction rates. How fast a reaction occurs is an important thing. Some reactions are very slow, some are very rapid. And how quick a reaction occurs depends on a number of things. The first is the concentration. If you have very small amounts of one of the reactants, it's going to go slow. If you have higher amounts of the reactants, it's going to go faster. Temperature is another big one. Wow. It says it's 69 here, and I'm sweating like a horse running hard. Temperature. Have you noticed that sometimes if the weather's cold, it's hard to start your car?
Yeah.
Have you thought about why? It's too frozen. That's a very technical answer. The reason is generally because the reaction going on in your car battery, remember we talked about last class period there being an acid that's causing a chemical reaction? That reaction is affected by temperature. So when it's cold, the reaction going on the battery is slower, which means that the car can't provide as much current, as much electricity to start the car. So it's not that your cylinders are frozen. It's not that the oil is thickened, because oil actually shouldn't thicken very much, and you actually don't really have oil in your engine when you start it cold. It's because the battery is cold, and thus the reaction rate has slowed down. Yes, Grace.
Doesn't that have to do with, like, the molecules can't move as much because it's cold, and so then they can't move together to form reactions?
I'm sure there is. Well, there actually definitely is, but it's not as much how fast they're moving; it's how much energy they have when they collide.
So,
But it's still relevant.
so I should take that out of the homework, or can I keep it? There was a homework question I didn't get that.
There's no question about that. It's because of how much energy they have when they collide. That's
Okay, so
the
it's
reason.
not-
I mean, it's still going to affect things. If they don't collide as often, it's also going to slow it down. But the primary one is when they collide, they don't have enough energy. Okay, so it's time to stop. Everybody have a great day, and I'll see you again tomorrow.